Thermochemistry. Now, what is thermochemistry? Simply put, it's the study of changes in heat. It's that short. Now, let's expand this with an example. Let's say we have wood, and we've been using wood for the longest time since the beginning of time as a fuel source, and it has a certain amount of energy content, and this energy content will decrease when you use it, right? So the wood is going to produce something when you burn it, and when you burn it, again, there's different types of wood. There's hard, dry mass, and then there's soft mass as well. The hard ones for the wood are a lot better to burn, gives a lot more energy. That would be trees like maple, oak, birch, etc. And the soft mass don't do nearly as good of a job. That would be like spruce or fern. They don't do as good of a job because they don't have as much dry mass packed tightly within them. So the amount of hydrocarbons that pack a good amount of potential energy is not as abundant in the soft ones. So the hard mass of the wood burn a lot better. So if this energy content decreases, it's going to release heat and light. And when it releases heat and light, these products are a result of the change in energy. So how much energy was in the wood? Well, we can't really know how much energy is in the wood, but what we can do is measure how much energy got transferred from here to here. This is something that we can do. Before we look specifically at those kind of examples, let's have a look at a more general view. If we were to look at this as a system, and this is what we've released in our surroundings, how does this system and this surrounding correlate? Let's have a look at example here with a system, and it's going to add with our surroundings. If we have a certain system in our surrounding, this is pretty much the universe. Because let's, for example, take a Earth that we are living on, and the surrounding is everything around the Earth, like the space. You get these two together, it gives us the universe. Now, in a system, in a surrounding, we are right now dealing with matter. So the laws of conservation of mass. This is where we did the balancing of equations. Rather than looking at that, the law of conservation of mass, let's look more towards the line of the first law of thermodynamics, which would be energy. Now, energy also needs to be conserved as well, just like matter. The energy of a system, so if we were to write the E of the system, can be added with the E of the surrounding, which is equal to the E of the universe, the energy. So all of these are still conserved because we're not looking at a realm of energy rather than matter. Now let's take this a step further. If we are looking at energy, what did I say up here? We are not able to figure out how much energy this has. The only thing we can do is burn it and see how much energy gets released. That change of energy, which we'll look at later at enthalpy, is how we determine how much energy is in here. It's kind of like how we determine the calories, how much energy peanut butter has. You just put it into a bomb calorimeter and it's going to release energy after you heat it up. That's how we determine its calories. Now let's look at these. If we're not going to look at the total energy, the absolute value, we'll have to look at the change. So let's have the change of this plus the change of this should equal the change of this. So I'm going to put this symbol as delta. This is the change. So the change of energy of the system that's in question plus the change of energy of the surrounding, so how much gets released out in the air, is going to equal the change of the energy of the universe. This means our change of energy of the universe, we can actually quantify it as a number. Now, the first law of thermodynamics states that energy cannot be created or destroyed. So this change of energy here must equal this. And it cannot change. It needs to be constant. So let's write this out again. Because whatever happens with our system here, and whatever happens with our surrounding over here, they can fluctuate up and down. This can go up, this can go down, this can go up, this can go down. It doesn't matter. They are going to be a sum. They're going to add together, because regardless of what happens, these two still equal the universe. So these can change around. They can fluctuate, but they will be conserved. These two together will always equal the universe. So the universe will never change. It's always going to be a balance between these two in equilibrium. This means that it's going to be constant. There is going to be no change. We said here that there is a change, but there isn't going to be a change. It's going to stay constant. What's going to change are its variables that it encompasses. That's it. So if this is going to be constant, what numerical value denotes constant? Well, if it's not going to change, it has to be 0. If it's any other number, 1, 2, 3, 4, 5, this is a change. So it has to be 0, so that there's no change. It has to be constant. So we can actually rewrite this way. The change of energy of the system plus the change of energy of the surrounding is going to equal 0. If that's the case, we can actually change this around, because we can actually start putting this on the other side, or this one on the other side. So let's say I take this one away. So right now it says the delta E system. This is a positive value. So if I change this to a negative value, all right, these two cancel out. But if I do it on the left side, I need to do it on the right side of the equal sign. Again, this is the left side, so I need to do it on the right side. So I'm just going to change that. Okay, what do we end up ending off with? Change of energy of the surrounding is equal to the negative change of the energy of the system. Now, you can multiply this by -1 and do the same thing on this side, and then it can actually change into this one as well. They mean the same thing. What happens on one side is going to give it to the next side, and what happens on the other side is going to give it to the other side. What do I mean by that? So this system here is exothermic and gives off energy, because it's a negative value here. If it gives off energy, where is it going to go? Let's say this is the Earth. Where is it going to go? It's going to go off into the surrounding. Okay? And if the surrounding receives that, guess what? One day, eventually, the energy of the surrounding is going to go back into the system. And you have these two happening back and forth simultaneously. But let's just talk a little bit about Q though. If it's the total absolute value of the heat quantity, it's going to be the heat quantity lost or gained. Again, it's going to be difficult to find this because we care more about how much heat got transferred as opposed to the total amount. But let's work with this for a sec. So Q is equal to the heat quantity lost or gained. So technically, Q would actually equal delta H. Now what is delta H? Delta H is the energy change in a reaction. Now, this is trying to make everything a lot more simple, because earlier on in the video, I said that this is not going to be possible to find. It's too rudimentary, too much tedious work, it's very difficult. So rather than using path functions, which would be this way, figuring out the total amount of heat that's present throughout the process of whatever reaction is going on, we're going to take this approach instead, which would be known as a state function. Now, this state function and path function I'll discuss shortly, but what's important here is that we're going to make these equal, because this is out of the question. We care more about the energy change. It's a lot more viable, it's a lot more useful. When a reaction occurs, heat is transferred between substances. This will be between substances. So that would be like kind of what we looked at here, our delta E of the system being equal to the negative delta E of the surrounding. Whatever is being released over here, that's equivalent to our enthalpy, the energy change in the reaction. Whatever energy this gives off, let's say exothermically, it gives off energy, that energy is now going to go into the system. And now this system can be abbreviated as the total amount of heat quantity that has now gained that energy. In this case, it would be gained, right? It didn't lose it, gained it, because the surrounding gave it to the system. So another way to put this is technically our Q here could equal negative delta H. Now let's break down Q a little bit more, because earlier on I just talked about how Q and delta H can be equivalent. Well, we have to look at Y. So the Q over here equals delta U plus W. Well, how does these two variables make Q equivalent to delta H? The reason why is, first we need to look at what they represent. Delta U just equals the change in internal energy of a system. And this W here is simply just work done by the system. If I were to break this apart, what's important for us to understand here is, what does this work done by the system means? This one should be quite obvious right now. Delta U, it's the change of internal energy. So again, energy is just represented as E, right? So this change of energy, as we kind of looked at before, which was enthalpy, how much energy is being given off, being transferred from one substance to another. So if I were holding, let's have a look here, maybe like ice, okay, and then you put it on your hand, what's going to happen? Well, this ice is going to be getting some energy from your hand because it has a lot of heat from your hand, and it's going to spontaneously go into the ice cube. We'll look more about spontaneity when we get to the third law of thermodynamics. Today we'll just look at the first one. This heat goes into the ice. How much change of energy occurred? Well, however amount of heat from your hand that went into the ice now receives that heat. So that change difference from here to here is that change of internal energy. So that's quite simple. how much energy is going from one place to another. And Q here, it's just the total amount of energy. So maybe I'll label this here. Total quantity of heat gained or lost. So this seems pretty straightforward. This seems pretty straightforward. So then what does it mean by the work done? If we have to rearrange this, so we can just, change it where this is isolated, so we can just do negative W so that this positive W cancels out, so we can put a negative W here, so it ends up just becoming Q minus W, or negative W plus Q, doesn't matter. So if I rearrange it this way, Q minus W, what happens as a result of this change in internal energy? If this change in internal energy happens, something is going to happen with the work. I'm going to change this W into pressure times the change in volume. Now, why do I do that? Well, pressure is always going to remain constant. Maybe I'll write this here. Pressure remains constant. It remains constant because in a lab, the open vessel container, whatever happens, the pressure on the inside is going to be constant with the pressure on the outside, because the universe is going to have an atmospheric pressure that's going to be the same on the inside. It's going to remain conserved. And we don't really care about the pressure of the universe. That's kind of too out there. It's okay to represent the lab as the universe. So the pressure is always going to be the same. In an open vessel container, it's going to remain the same. It's not going to change. The volume will change though. Let me give you an example as to why. If you had, let's say, a piston over here, and this piston, let's say it has some sort of lid, and let's say it's frictionless, and on the inside of this lid, let's say there's some sort of reaction, okay, over here. Now when a reaction occurs, it's gonna push this lid upwards. So this happened in the beginning, and then let's say this is the same thing in number 2. Now this lid is up here now because of that reaction. So that is going to increase. So again, the reaction is going to happen. It's going to push it upwards. So now this is where it used to be. Now it's up here. So that change is going to be represented as delta V, the change in volume. The pressure needs to be maintained though. The pressure remains constant because there's a certain amount of pressure here. But if a reaction occurs, of course, the amount of vibrating particles are going to start colliding with one another more in an excitable manner. So the pressure is not going to stay the same. How can pressure stay the same? It's if the volume increases, indirectly proportional. So if the pressure increases, the volume needs to increase to maintain that pressure as staying constant. That's why the P here doesn't have a delta on it. Now, as this reaction occurs, to maintain this pressure of the container, the volume must increase. Therefore, there's negative work that's actually being done, because there is work being done from the system, but since the energy is going upwards, outwards from the system, it's technically a negative value because the system is doing work towards the outside. Now let's jump back to this formula. Now that we understand what's happening with the work, with pressure and the delta V, we can rearrange this in a way where we understand at the beginning of this video how Q is going to equal delta H. The reason why, I mean, you know what, let's rearrange this so that this Q, this goes on this side. So you end up getting delta U plus P times V. So this is a U here. So if you rearrange it this way, so I know this is a negative P times delta V, so if you just added a plus P times delta V, that, I mean, those both cancel out and you have to do it on this side. So that's how I got this. This is showing us that this delta U and this variable of P times delta V are a state or a path function. The state function is what we want. So a state function doesn't rely on the path taken between the final and the initial. It only cares about the final and the initial difference. Delta U here, the change in internal energy, is a state function. Pressure and change in volume are also state functions. So both of these here are actually state functions. It only cares about the difference. About the difference between the final and the initial. Whereas in a path function cares about the path taken. From that final and the initial. It cares about that. So when we look at path functions, that'll be like the radiant energy, the electricity. For our case, in this concept, in this video, there's no need to look at that. It's tedious work that's not very useful. So we care more about state functions. All of these are state functions. So if they're state functions, Q is not a state function. Q is an absolute value. So we need to change Q into delta H. So we can actually say delta H. Even though it's equivalent to Q, it's a state function. So all of these here are state functions, which is what we really care about. So technically, we could change this into our final formula as delta H is equal to delta U plus pressure times change in volume. But remember, whatever occurs in this formula, this change of internal energy plus the sum of this constant pressure and the change in volume, the work that's being done and being spread out into the surroundings is going to be absorbed by something. What is it going to be absorbed by? It's going to be absorbed by Q, the surrounding object, whatever is taking this change of energy. Because remember, delta H, our enthalpy, is this change in heat. So this change with this and this is going to be given off somewhere to an object, to a surrounding. And we can measure how much of this gets transferred. How much of it did it get transferred? It's going to be transferred to Q. So this is why, in the beginning of this video, this delta H and Q, why are they represented in this fashion as being equaled? Because even though this is an absolute value, we can measure this, which is more important to us, our state functions over here, measure how much is being released, and whatever is being absorbed on that other object, that next medium, that is what we can quantify. And that's how much quantity of heat here, gained or lost, is important to us.